The universe looks quiet, but that silence hides events of unimaginable power. A star can burn steadily for billions of years, and then, in just a few seconds, erase itself in a catastrophic explosion. We call these events supernovae, and a supernova is not simply a star's death. It is one of the most powerful energy releases the universe has ever produced, so intense that for a brief moment, a single dying star can outshine every other star in its entire galaxy combined. But here's what's strange. Astronomers have been studying supernovae for centuries, and we still don't fully understand how they begin. Because catching a supernova at the exact moment of detonation is nearly impossible. Or at least it was, until very recently. Today, we're going to examine the historic moment humanity caught a supernova in the act for the very first time, and for perhaps the first time ever. We'll get close to answering these questions. What is actually happening inside a star just before it explodes? Why does the core collapse inward and then explode outward? And why do some supernovae fail before they ever get started? If you're ready, we're going back to the moment one of the universe's most violent cosmic events was born. Supernovae are still filled with profound mysteries. Even today, scientists have not fully resolved the exact mechanisms that trigger these explosions. One major reason for this is that supernovae are completely unpredictable. Astronomers know which types of stars will one day explode, but pinpointing exactly when is nearly impossible. As a result, most of the supernova data we have doesn't come from the explosion itself, but from studying the remnants left behind. Most of the time, astronomers examine a supernova hundreds or even thousands of years after the fact. Or sometimes, they catch one purely by chance, simply because they happen to be looking at the right patch of sky at the right moment. But there's an important turning point here. In early 2024, that changed. For the first time in history, humanity managed to catch a supernova at the very moment it detonated. And this time, it wasn't pure luck. It happened thanks to a deliberate observational program. Astronomers detected the explosion just a few hours after it began. This stands as one of the earliest supernova detections ever made. And what those observations revealed was something scientists had never seen before: the true geometry of the explosion itself. At first glance, that might sound like a minor technical detail, but in reality, this discovery plays a key role in understanding the internal structure of exploding stars. Because with this data, scientists can now pursue answers to these questions. What are the mysterious physical mechanisms that set supernovae in motion? Why does a star's core first collapse inward and then explode outward? And why do some supernovae simply fail? Thanks to this new data, astronomers are closer to answering those questions than ever before. On the night of April 10th, 2024, a routine sky survey was underway. The system conducting it was the ATLAS survey, a network of 4 wide-field telescopes positioned at different points around the globe, in South Africa, Chile, and 2 locations in Hawaii. Thanks to this global network, the ATLAS system can sweep the entire night sky in roughly 48 hours, with each region of the sky imaged 4 times within that window. These rapid repeat observations allow astronomers to catch sudden, fast-evolving cosmic events. And at 3:21 a.m. on April 11th, 2024, that's exactly what happened. The ATLAS telescopes detected an unusual brightening in the sky, a single point that had dramatically increased in brightness over the previous 5.8 hours. The data immediately triggered the telescope's automated alert system. This newly discovered transient, as astronomers call a temporary light source, was broadcast to observatories around the world. Astronomers got to work immediately. What was this signal? The answer emerged quickly. 23.8 million light-years away, in a spiral galaxy called NGC 3621, a star had just died. What ATLAS had caught was a Type II supernova, a massive explosion triggered by the collapse of a high-mass star's core. One of the research teams that analyzed this discovery was led by astronomer Ye Yong from Tsinghua University in Beijing. They immediately recognized what this could mean. For the first time in history, this event might offer humanity a chance to study the true geometry of a supernova explosion in real time. But they had very little time. Critical hours. The first moments of a supernova are extremely brief. The true geometry of the explosion is preserved only during the initial few hours. After that, the material ejected by the blast collides with surrounding clouds of gas and dust, and those collisions distort and obscure the explosion's original shape. If astronomers don't act fast, the pristine physical signature left by a star's death is lost forever. So the team had to move immediately. While most of the world slept, Ye Yong and his colleagues worked through the night with a single goal: to point one of the most powerful telescopes on Earth at this explosion. That telescope was the Very Large Telescope, the VLT, operated by the European Southern Observatory in Chile. The team submitted an urgent observation request, aiming to measure the geometry of the explosion before it was gone forever. Fortunately, the European Southern Observatory approved the request quickly. The VLT was immediately redirected toward NGC 3621. The researchers waited at their screens. This was a genuinely critical moment. Had they arrived too late? Or would they capture the undistorted geometry of the explosion? Luck was on their side. When the data began arriving, the team realized they had succeeded. They had captured the explosion's original geometry intact. Ye Yong and his team were now observing what they named SN 2024 GGY in its very first moments. And for the first time, they were one step closer to understanding how the universe's most violent cosmic explosions actually begin. Type 2. Supernovae. What's really happening inside a star? Supernovae are broadly divided into two main categories, but here we'll focus specifically on Type 2 supernovae, because that's exactly what Yong and his team observed. Type 2 supernovae are among the most dramatic and energetic events in the universe, occurring at the end of the lives of massive stars. Today, we have a fairly robust model for how stars die. This model was built from the combination of physical theory, telescope observations, and advanced computer simulations, meaning that our understanding of stellar death has been made possible not just by looking through telescopes, but by constructing virtual universes inside computers. Modeling is an extraordinarily important tool in science because it allows researchers to test ideas and understand processes we cannot yet directly observe. And critically, building these models requires not only astronomers, but people with advanced programming skills as well. Scientists and software engineers effectively function as the two wings of modern astronomy. This reflects a truth often emphasized in the scientific community. For anyone who wants to understand the universe, coding has evolved from a useful tool into an instrument as essential as the telescope itself. The fundamental job a star performs throughout its life is based on a simple principle: converting lighter elements into heavier ones through nuclear fusion. In this process, atomic nuclei merge into more stable configurations, releasing excess energy. That energy generates an outward pressure from deep inside the star, and this pressure plays an absolutely critical role, because inside a star, two enormous forces are locked in constant opposition. Gravity tries to crush the star inward. The energy produced by nuclear fusion pushes outward. When these two forces are in balance, the star maintains a stable, spherical structure. In other words, every star we see in the night sky is a cosmic balancing act sustained across billions of years. As time passes, the fusion reactions in the star's core begin producing progressively heavier elements. Climbing the periodic table like a ladder. The transformation chain proceeds roughly as follows: hydrogen to helium, helium to carbon, carbon to oxygen, oxygen to neon, neon to magnesium, magnesium to silicon, and silicon to iron. This process continues for millions, sometimes billions, of years. But there's a critical endpoint. the chain terminates at iron. Iron may seem like an ordinary element, but in nuclear physics it occupies a uniquely final position. Iron has the most stable nuclear structure of any element, the lowest mass per nucleon of all atomic nuclei. What this means in practice is that when a star attempts to fuse iron into something heavier, it no longer releases energy. It consumes it. Converting iron into heavier elements requires the star to spend energy rather than produce it, which means the star's energy generation mechanism has effectively broken down. In other words, the moment iron begins accumulating in a star's core, one of the universe's great countdowns has begun, because the delicate balance that has sustained the star is about to collapse. As fusion reactions slow and stop, the outward pressure weakens. Gravity seizes the advantage, and at precisely that moment, one of the universe's greatest explosions is about to be born, a supernova. Eventually, that long nuclear transformation chain in the star's core reaches its inevitable end. Most of the core has been converted to iron, and iron, in terms of stellar physics, is a dead end. No energy-producing fusion reactions remain. The nuclear furnace at the heart of the star begins to go dark. When fusion ceases, the outward pressure disappears with it. The balance that held the star together for billions of years shatters in an instant, and one of the most violent processes in the universe begins: core collapse. Gravity now meets no resistance. The core begins collapsing inward at incomprehensible speed. The outer regions of the core can reach velocities of roughly 70,000 kilometers per second, approximately 23% of the speed of light. The idea of matter inside a star falling inward at that pace is the kind of cosmic catastrophe the human mind struggles to fully grasp. As the collapse accelerates, the density at the core reaches extraordinary levels. Pressure builds until even the internal structure of atoms cannot hold. At this point, something extraordinary occurs. Protons and electrons are forced together and fuse, forming neutrons. This process is known in physics as inverse beta decay. The result is an incredibly dense structure forming at the star's center, composed entirely of neutrons. A neutron core. But neutrons aren't the only product of this transformation. At the same moment, vast quantities of neutrinos are released into the universe. Neutrinos are particles with nearly zero mass that interact with almost nothing, yet they are produced in such enormous numbers that they carry away the bulk of the star's total energy. In fact, approximately 99% of the energy released in a supernova explosion is carried away by neutrinos, particles invisible to virtually everything. It's a strange thought. As one of the universe's greatest explosions unfolds, nearly all of its energy disperses into space in the form of particles that interact with almost nothing at all. The shock wave. The collapsing stellar material eventually slams into the hyperdense neutron core forming at the center. And something remarkable happens. The matter bounces back as if it has struck a wall. In astronomy, this is called the core bounce. The collision sends a massive shock wave propagating outward from the star's center, racing through its interior layers at thousands of kilometers per second. At first glance, you might expect this wave to tear the star apart. But here's where things get interesting. Most of the time, it can't. As the shock wave pushes outward toward the star's outer layers, something unexpected happens at around 100 to 200 kilometers from the center. The wave stalls. The reason is the dense iron layers surrounding the core. As the shock wave passes through them, temperatures and pressures spike to such extreme levels that iron nuclei begin to disintegrate, breaking apart back into lighter elements and helium. But this disintegration process does something critical. It absorbs the shock wave's energy. The very force meant to destroy the star is dampened and weakened by the star's own material. And this is the moment that determines the supernova's fate. Two possible endings. From this point, the universe chooses between two scenarios. The first is failure. If the shock wave remains stalled for longer than roughly 1 second, the star's outer layers continue collapsing inward. The core accumulates more and more mass until it surpasses a critical threshold and collapses entirely. The result? A black hole. No explosion, no flash of light. The star silently transforms into one of the darkest structures in the universe. Astronomers sometimes call this a failed supernova. It is one of the most dramatic events the universe can produce, and no one would ever see it happen. The second is the actual explosion, but there is a more common, and still deeply mysterious, alternative. Sometimes the shockwave regains its strength. Something, and we don't yet fully know what, manages to re-energize it. Among the mechanisms scientists are investigating: neutrino flux, magnetic fields, internal jet currents, or some combination of all three. But to be honest about it, we still don't know exactly how this process works or what drives it. This is, in fact, one of the greatest unsolved mysteries in astrophysics, which is precisely why new supernova observations like SN2024GGY are so extraordinarily valuable to scientists. Every new explosion brings us a little closer to solving it. If the shockwave does regain its strength, it continues its journey, tearing through stellar layers thousands of kilometers thick. This journey is not a brief one. It can take hours for the shockwave to reach the star's outer surface. When it finally arrives and bursts through the outermost layer, the result is an extraordinary flash of light, one of the most luminous moments in the universe. As the shockwave exits the star's surface, enormous quantities of ultraviolet and visible light are released. The outer layers of the star heat to tens of thousands of degrees. This is the moment the supernova first becomes visible, what astronomers call shock breakout. Over the following week or two, the brightness climbs rapidly until the supernova becomes one of the most luminous objects in its entire galaxy. And the very first light that registers in an astronomer's telescope is exactly this: the light of shock breakout. In the early hours of April 11th, 2024, the Atlas telescope system had captured precisely this rising light. They named it SN2024-GIA. Atlas catching this supernova so early was celebrated as a major achievement. But it was, in truth, only the beginning. Because there is a critical reality about explosions. Once those first moments have passed, the original geometry of the star is gone forever. If you want to understand how an explosion began, you need to redirect your telescopes very quickly. That's exactly why Ye Yong and his team had fought urgently to secure observation time on the VLT, one of the most powerful telescopes in existence. But their goal wasn't simply to see the supernova. They were searching for a very specific signature hidden within the light, one that only a single scientific instrument could reveal. The hidden codes of the explosion, decoding the shape of a supernova through its light. To decode the secrets hidden in the light of SN2024-GGI, Yong's team used a specialized instrument mounted on the VLT called FORS-2, the only spectropolarimetry device available in the Southern Hemisphere. This instrument measures how light is polarized across different wavelengths. Under normal circumstances, light waves oscillate in every direction. This is unpolarized light. But when light oscillates in only one specific direction, it is said to be polarized. Think of sunlight reflecting off a water surface or glass. It becomes polarized. FORS-2 measures these directional oscillations in the light from a supernova to reveal the shape of the explosion. Why does this matter? If the explosion were a perfect sphere, light would radiate equally in every direction, producing no detectable polarization. But if the explosion has axial symmetry, elongated like a rugby ball or a peanut, then the light becomes polarized in a structured pattern. And that is exactly what FORS2 measures. The light first passes through a rotating crystal plate, allowing the direction of polarized light to be precisely adjusted. It then passes through a Wollaston prism, which splits the light into two separate polarization components. Each beam is then dispersed into its component wavelengths, producing two spectra side by side on the detector. By comparing these spectra, scientists can calculate the direction and degree of the light's polarization, and the result reveals the geometry of the explosion. That geometry, in turn, allows researchers to infer which mechanism triggered the blast. For the past 50 years, astronomers have been trying to identify the mechanism that re-energizes the stalled shock wave. Two leading theories dominate the field. The first is the neutrino-driven model. As the core collapses, it fires an enormous quantity of neutrinos into space. In the dense region just above the core, even neutrinos struggle to pass through. But a small fraction deposit their energy into the surrounding matter, driving intense convection upward from below. If enough energy accumulates, the shockwave revives and the star is, in essence, blown apart from within. Crucially, these explosions are irregular and asymmetric. 3D simulations and observational evidence, such as the radioactive element distributions of Ti-44 and Ni-56 found in the Cassiopeia A remnant, confirm this asymmetry. The second is the jet-driven model. In this scenario, a rapidly rotating neutron star formed during the collapse, together with a surrounding disk of material, generates powerful magnetic fields that launch two high-energy jets. These jets bore through the star's envelope, channeling the explosion along an axis and producing an elongated football or olive-shaped blast. This structure had previously been observed in some supernovae, including SN2023-IXF. And so the critical question becomes, which model does SN2024-GDGGI support? If the light appears irregular and asymmetric, the neutrino-driven model is favored. If the light shows axial symmetry, the jet-driven model wins. At this point, I want to put a question to our extended viewers. What do you think? Did SN2024-GGI explode with irregular asymmetry or with axial symmetry? Share your predictions in the comments. The spectropolarimetry data obtained with FORS2 on the VLT revealed a clear, elongated, axially symmetric explosion, technically described as a prolate ellipsoid, shaped like an olive or a rugby ball. Initially, this appeared to be strong support for the jet-driven explosion model. A neutrino-driven explosion should have been entirely asymmetric. The observational verdict seemed to be in. Case closed, right? Unfortunately, the universe rarely keeps things that simple. Our theoretical models are built on physics, simulations, and data from past supernovae. But data obtained after the critical early window has closed is inherently limited. The neutrino-driven model has gaps. A 2015 paper published in the monthly notices of the Royal Astronomical Society showed that 3D neutrino simulations produce explosions roughly an order of magnitude weaker than what observations actually require. Neutrino heating alone is not sufficient to explain the full power of a supernova, but the jet-driven model is not without its own problems. In 3D simulations, introducing even a 1% perturbation along the rotational axis of a rapidly spinning, highly magnetized core causes the jets to become unstable. Rather than cleanly driving through the star, the energy disperses into twisted, folded lobes, and the explosion never happens. So, how did SN2024-GGI manage to explode? Clearly, there is at least one additional mechanism at work. One possibility: these oscillating, chaotic jets, unable to efficiently transport energy along the axis, as in the classical model, instead accumulate energy near the core, generating shock waves that form hot, high-pressure bubbles which push the stellar material outward and initiate the explosion. The jets exist, but the overall geometry of the explosion still preserves axial symmetry. exactly as seen in SN 2024 GGI. What this tells us is that supernova explosions can exhibit organized axial symmetry. But how that symmetry arises remains unresolved. Is it narrow, oscillating jets, a magnet-R rotation mechanism? Something else entirely? We don't know yet. And what role do neutrinos play? For stars like Cassiopeia A with asymmetric explosions, is the mechanism the same or different? Answering these questions requires more data. New all-sky surveys and next-generation telescopes are now enabling astronomers to detect supernovae within 24 hours of detonation. Projects like ATLAS, the Vera C. Rubin Observatory, NASA's UVEX, and the Sloan Digital Sky Survey are accelerating this process considerably. SN 2024 GGI has shown us that our models still have gaps, but the observations ahead may help us find the missing piece and understand with greater precision than ever before the final breath of the stars. And that, my friends, is where the real wonder lies. Every new observation peels back a little more of the mystery surrounding the universe's most violent explosions. Sometimes chaos, sometimes order, but always astonishing, always thought-provoking. Even in its most brilliant light, the universe still guards its secrets. We can now catch them in the act. But to understand them completely, it seems we still need a little more time. If you found this valuable, I'd love your support in the comments. Take good care of yourselves until the next video.